Hello everyone, welcome back. Today we are going to continue our discussion on the equation of changes or the equations of change. And we're going to look at a very important topic today, which is the dimensional analysis of the equations of change for non-isothermal systems. And we will also look at the analogy for multi-component systems. Okay? So let's go ahead and get into our contents today. Let's first look at the dimensional analysis for non-isothermal systems. And to kind of simplify our discussion, let's make some restrictions to the properties of the fluid. So for simplicity, we will restrict to fluids. Simplicity, we will restrict our discussion to fluids with constant viscosity. So with constant fluid properties like viscosity, like thermal conductivity, and heat capacity. Okay, so we'll put a parenthesis around it. Okay, so whenever we want to use the equations of change to look at or analyze different systems, typically we would list down three equations. So one is the equation of continuity. So that's just the overall mass balance. The second would be the equation of motion. So we're going to be looking at the fluid flow, okay, the velocity profile of the flowing liquid or fluids. And for non-isothermal systems, we will also add in the analysis of equation of energy. So it's an equation that deals with temperature. Okay, so let's list these three equations down. So first we have the equation of continuity. And the equation of continuity is simply saying that the gradient of your velocity is going to be 0. Okay. And then let's look at the equation of motion. So the equation of motion is basically saying that the substantial derivative of velocity, which includes the time-dependent term and the convective terms, equals to the negative gradient of pressure plus the viscous dissipation, so viscous forces. So mu times the Laplacian, so the viscosity times the Laplacian of velocity. And then you have external forces. And when you have external forces, typically it's gravity, we would also want to consider buoyant forces. So we would put in the rho bar g and the buoyant coefficient times t minus t bar. So remember that we're dealing with non-isothermal systems. And there is a chance that a non-isothermal system will give rise to free convection if you don't have a really strong, like a pressure gradient to pressure drop to drive the fluid flow. Okay? And so here also we want to make a note that we're actually combining the rho term and the p term. So let's just make this really clear. So let me erase this a little bit. We're going to use a capital P here. And the capital P here is actually a combination of the pressure plus the potential driven by gravity. So it's going to be rho bar times G times H. Okay, And now let's continue. So finally we have the equation of energy. So we have rho, sorry, I should put a bar here too. We have rho bar Cp, the substantial derivative of temperature on the left hand side. This equals to the thermal conductivity times the Laplacian of temperature, and plus, if it exists, we would still have the viscous dissipation or viscous work that's contributing to energy transport. Okay, so here are our three equations of change listed down for non-isothermal systems. And you can see that it is now, its current form is not a dimensionless form. So we want to, what we're going to do here is we want to change all the equations of change into dimensionless forms. And to do that, what we first have to do is to define some characteristic quantities to make each term dimensionless. Okay, so now let's take a look at that. So having these three equations listed down, let's take a look at the characteristic quantities to make these equations dimensionless. So characteristic quantities to make dimensionless. So let's take a look at what are the dimensionless quantities, right? So you can see in the equations here, what do we have? So we must have some coordinates or some dimensions in physical parameters like x, y, and z, right? So you may have fluid or heat. You may have momentum or thermal transport or energy transport in different directions. So we want to define some characteristic length first, right? So let's just put the first one as, characteristic length. Characteristic length. Okay. So typically, if your system has a fixed dimension, let's say it has a fixed length of L naught. So let's say it has some fixed length of L naught. So let's also parenthesis that this is a fixed dimension. Then we will define our dimensionless XYZ coordinates accordingly. So we would define the dimensionless quantity typically we would use let's say the quantity is using a Q symbol. For dimensionless, we would put a check mark on that symbol. Okay, so in this case the dimensionless quantity would be our XYZ coordinates, and we will say that we have the dimensionless x equals to the actual distance in x over our characteristic quantity. So here you see that the unit would be canceled out. So there are no units, because the units of the numerator and the denominator cancels out. Okay, so similarly we would do the same for our y and z. So we have y over L naught, and we have z, dimensionless z equals to z over L naught. Okay, and also you can see that in the equation of changes we always have the time dependent term. So we also need to define a dimensionless time. So let's use a different marker, different color pen. So we have characteristic time. Okay, and there are many choices you can use, but for simplicity, let's choose one that's most easyable to understand. So you can think of the dimensionless time being what? If the fluid has some characteristic velocity, let's say it's v naught. Okay, and so if you want to find a dimensionless time, the easiest one is v naught divided by some distance. Okay, so a combination of v naught with L naught gives you the characteristic time. And basically that would be what? That would be L naught divided by v naught, right? Because if you look at the units, what's in the unit would be what? You have distance over time, right? So the distance cancel out and you now have a characteristic unit of time. Okay, so our dimensionless time would be, again, t with a check mark equals to the actual time divided by L naught over V naught. So equals to V naught over L naught times T. Okay, so that's the dimensionless time, and simply speaking, if we have a characteristic velocity V naught, so characteristic velocity, let's say we have some, plug flow coming in or some Vmax, whatever, and let's just call that V naught for now. Okay, so you would have your dimensionless velocity as, we should always don't skip steps. We have the dimensionless velocity v with a check mark equals to the actual velocity over v naught. Okay, let's further look at the terms and the equations of continuity. So let's look at pressure. So if you look at the pressure, we can define some characteristic pressure. Okay, and the characteristic pressure basically can be oddly defined, or not as intuitively known, but we typically define our characteristic pressure using the density of the fluid multiplied by the square of the characteristic velocity. Okay, so the dimensionless pressure would be P with a cap with a check mark equals to P minus P naught over our characteristic pressure. So we have, if we go back to our equation of changes, we have dealt with velocity, we have dealt with the dimensions that you would be using in the gradient operator, and we have dealt with time in the substantial derivative. We've dealt with pressure, velocity, dimension again, and now the next one would be trying to deal with temperature. So let's continue our discussion here. So if you think of a characteristic temperature, typically you would use what's defined in the boundary condition. So typically we would think that the characteristic temperature can be, some T1, some T0 at the boundary, or it can also be defined as T1 minus T0. So depending on the the mathematical formula you would use, but let's just give you some example of typical what we get. So the dimensionless temperature again, we define it as T with a check mark equals to the actual temperature minus one of the boundaries over the difference between the two boundaries. Okay, now so let's further move down with our equation of changes. We have dealt with equation of continuity, equation of motion, and finally we need to deal with the equation of energy. So let's take a look at the stress tensor here. So the viscous shear stress tensor, so I should say dimensionless, I should say shear stress tensor, or maybe I should say characteristic shear stress tensor. Or we'll just give you the result here. So the dimensionless shear stress tensor equals to L naught over V naught square times the actual shear stress tensor. And finally, let's look at the operators. So the gradient operator. Dimensionless gradient operator. So we have the dimensionless gradient operator equals to the characteristic length times the actual gradient. So gradients, remember that it's like d dx plus d dy plus d dc, and it has a unit of L naught over 1. So by multiplying it with L naught, you make it dimensionless. And also we will want to define the dimensionless substantial derivative. So the dimensionless substantial derivative, d over dt, equals to L naught over V naught times the substantial derivative. Okay, so I hope you're not getting lost here. Again, let's kind of review what we're doing here. Our objective here is to formulate or make the equation of changes for a non-isothermal system having the equations of continuity, the equation of motion, and the equation of energy, making it into dimensionless form. To do that, we first need to figure out the characteristic quantities to make each term in the equation to become dimensionless. Okay, so we start by looking at the characteristic length. And the reason you want to use that because you need the characteristic length to make a lot of terms, especially the gradient operator and the substantial derivative terms, making it dimensionless. Okay, so you can use the characteristic length to define your dimensionless xyz's. Okay, just divide the actual xyz by the characteristic length if your system has a fixed dimension. Then we can, if the fluid has some characteristic velocity, let's call that V naught, then we can define the dimensionless velocity simply by dividing the actual velocity with V naught. And using the relation between V naught and L naught, we also can define the characteristic time and also the dimensionless time, which is the actual time multiplied by V naught over L naught. Then we define the characteristic pressure using rho V naught squared using the boundary conditions to define the dimensionless temperature. Again, we should probably say that this is an example for fixed boundary problems. Example for fixed boundary problems. Okay. And then we also define the dimensionless shear stress tensor if you have some non-negligible work generated by, very fast-moving fluids having a large velocity gradient. And then most importantly, we define the dimensionless gradient operators, which is the original operator multiplied by L naught, and also the dimensionless substantial derivative. Now, we're going to use this information to make the equations of change dimensionless. Okay, so now let's see how we can, make the equations of changes into its dimensionless form. Basically, we just need to change all the terms to dimensionless. So let's, say change all terms to dimensionless. And how does that work? Let's take a look at the most simple case of the equation of continuity. So equation of continuity. So for the equation of continuity, we have the, gradient of velocity equals to 0, right? But the gradient equals to its dimensionless form. The gradient operator equals the dimensionless form gradient operator multiplied by or divided by L naught. Or am I doing this right? Let's see. Yes, so the gradient operator equals to this divided by L naught. And we also have the velocity profile equals to what? Equals to the dimensionless velocity multiplied by V naught. Okay, so if we plug these back into our equation of changes, what we see is the following. We see that we have the dimensionless gradient operator divided by L naught multiplied by the dimensionless velocity times the characteristic velocity equals to V naught over L naught. Sorry, this naught should be subscript. Times the dimensionless gradient dot product of the dimensionless velocity. Okay, so we still have a conclusion that the equation of continuity in its dimensionless form would be the dimensionless gradient operator dot product with the dimensionless velocity equals to 0. Okay, so that's the equation of continuity. Let's use, red box to check it. Now, for the equation of motion, we need to, again, do this for each term. So equation of motion. So let's first look at the left-hand side. On the left-hand side, what we have is we have rho bar times the substantial derivative of velocity, right? So this is our left-hand side. So basically, let's take a look at what happens here. So the substantial derivative now equals to the dimensionless substantial derivative times V naught over L naught, right? So you can see that it's coming from here. And also we have the velocity equals to the dimensionless velocity times V naught. Okay, so this would be the left-hand side. And now let's look at the right-hand side. On the right-hand side, we have pressure. So pressure equals to the dimensionless pressure times rho bar and V naught square plus P naught. And then we have the Laplacian operator. So the Laplacian operator equals to the dimensionless Laplacian operator divided by L square, or L naught square. Okay, and then we have the temperature term. So the temperature equals to a dimensionless temperature times T1 minus T naught plus T naught. Now we want to plug these back into our equation of motion, right? So on the left-hand side, we now have rho bar, excuse me, times V naught over L naught times the dimensionless substantial derivative of the dimensionless velocity times V naught. So that equals to rho bar V naught square over L naught times the substantial derivative of the dimensionless velocity. Okay, so this would be our left-hand side. So left-hand side. On the right-hand side, what we have now would be what? So the first term would be, we have the negative gradient. So the negative gradient would be the negative, let's see, L naught over 1 times the substantial gradient operator times the dimensionless pressure times rho bar V naught square plus P naught. And then we have the viscous term, so we have plus mu over L naught squared times the dimensionless Laplacian times V over V times V naught. And then we have the last term would be minus rho G and the buoyant coefficient times T minus T bar, right? So T minus T bar would be down here. We have the dimensionless temperature times T1 minus T naught plus T naught minus T bar minus T bar, T1 minus T naught minus T naught. Okay, so if we kind of reorganize this, what we have is the following. We have negative V naught over L naught, and V naught is square here. And we can also take out rho bar. And you can see that the P naught is a constant, so it vanishes in the gradient operator. So this one actually vanishes. So we only have the substantial gradient operator times the dimensionless gradient operator times the dimensionless pressure. Okay, and the second term we also have V naught over L naught square times viscosity times the dimensionless Laplacian operator of the dimensionless velocity. And finally we have the T naught cancels out here. So finally we have what we have, rho G beta times the dimensionless temperature times T1 minus T naught minus T bar, dimensionless T1 minus T naught. Okay, so this is the right hand side. Now let's take a look at the left and right hand side. If we divide both sides by rho and V naught squared over L naught, what we see is that if we cancel rho out, then we have additional rho down here. The rho cancels out. Okay, and if we divide all by V naught squared cancels out. We have an additional V naught at the denominator again. Excuse me. We have a V naught squared down here now. And if we multiply everything by L naught, then this square cancels out, and then we have a L naught up here. So if we make the left hand side just the dimensionless, substantial derivative of the dimensionless velocity, here is what we get. We have dV with a check over dt, so substantial derivative of velocity, all in dimensionless form on the left hand side, now equals to the negative, the dimensionless gradient operator multiplied by dimensionless pressure, plus the viscosity over rho bar velocity, characteristic velocity V naught and L naught, times the dimensionless Laplacian of the dimensionless velocity, minus G times the buoyant coefficient times T1 minus T naught times L naught over V naught square times the substantial temperature, the dimensionless temperature minus the dimensionless reference temperature. Okay, so this would be your final form of the dimensionless equation of motion. So this is our dimensionless equation of motion. So you can see that we have a rather simple format just looking at dimensionless quantities, but for the viscous term and the buoyant term, we have some properties, characteristic properties, or characteristic quantities grouped in the brackets, and we will look at these brackets later on. These are important implications, okay? Okay, and finally, let's look at the dimensionless equation of energy. So let's look at the equation of energy. So the equation of energy on the left-hand side, remember that we have rho Cp dt equals to thermal conductivity times the gradient or the Laplacian of temperature plus mu and the shear stress tensor. So again, let's take a look at how to make this into dimensionless form. So we have on the left hand side, we have rho Cp, then we have V naught over L naught times d dt times T dimensionless form T1 minus T naught plus T naught. Okay, so this equals to rho Cp V naught over L naught times T1 minus T naught d dimensionless t dimensionless lowercase t. So this would be your left hand side. On the right hand side, we have the thermal conductivity term or the conduction term. So this one is simple. This would be what? This would be the thermal conductivity times L square, or divide by L square. Let's make sure we're not ahead of us. So we should be, let's see. Yeah, sorry, should be dividing it by L square. So we have the dimensionless Laplacian divided by L square, again, times the dimensionless temperature T1 minus T naught plus T naught. So this equals to K over L naught square times T1 over minus T naught, and the dimensionless Laplacian times the dimensionless temperature. And finally, for the viscous dissipation term, we have mu and the shear stress tensor equals to mu times V naught over L naught square times the dimensionless shear stress tensor. So if we combine everything together, we now have, so if we combine this, we have rho bar Cp V naught over L naught times T1 minus T naught dt with the check mark dt equals to K over L naught square T1 minus T naught, the dimensionless Laplacian of dimensionless temperature, plus mu times v naught square over L naught square dimensionless shear stress tensor. Okay, so again, we want to make the left-hand side as simple, just remaining this. So we're going to divide all by this on the left-hand side. So what we get is the following. We have dt now equals to what? Equals to, we can cancel out the t minus t naught. So we have the thermal conductivity in the numerator. We have L being canceled out once. L naught, we have V naught rho Cp times the dimensionless Laplacian of the dimensionless temperature plus mu V naught cancel out once, and also L naught cancel out once. So we have L naught rho Cp T1 minus T naught times the dimensionless shear stress tensor. Okay, so let's rewrite every term for you again. So let's just say this would be our dimensionless equations of change. So first we have the equation of continuity. We have the dimensionless gradient of the dimensionless velocity equals to 0. Then we have the equation of motion, which is the dimensionless substantial derivative of the dimensionless velocity equals to the negative dimensionless gradient of the dimensionless pressure plus a dimensionless shear stress term. We have rho, we have V naught, we have L naught times the dimensionless Laplacian of the dimensionless velocity. And then we also have a buoyant term. So again, the coefficient is G beta T1 minus T naught times L naught over V naught square times T minus some reference T. And then we have our equation of energy. So we have, again, the dimensionless substantial derivative of the dimensionless temperature equals to some coefficient here. So K over L naught V naught rho Cp times the dimensionless Laplacian of dimensionless temperature plus mu V naught over L naught rho Cp T1 minus T naught, and the dimensionless shear stress tensor. Okay, so you can see that when everything's changed into dimensionless form, we have some interesting coefficients in the equation of motion in the brackets, right? We have the brackets, they're having some coefficients that must also be in dimensionless groups. Okay, so everything in that bracket add together must also be dimensionless, so it forms a dimensionless groups. And now let's take a look at these dimensionless groups in the equations. Okay, so let's take a look at that. That's going to be the most interesting part, because these dimensionless groups can be very useful. For example, let's take a look at the equation of motion. If we can know the numbers of the dimensionless groups in the brackets, then we can actually have an idea of the relative contributions of these terms in our equation of changes, whether they can be neglected or not. Maybe they are so small or they're overwhelming that the other term might be able to be negligible. And that can make us simplify our system a lot without introducing a lot of errors. Okay, so the dimensional analysis would be a very powerful tool or method for us to, have a very brief, a very quick idea on the system on whether what terms are dominating and what terms are not. Okay, so let's take a look at the dimensionless groups and the equations. Okay, so let's take, and there are kind of like 4 cases that we're going to, discuss here. So let's take a look at case 1, which is the most common case we would encounter. So case 1. Case 1 is looking at forced convection, which is probably the most common case encountered for chemical engineers. So forced convection. So that means the characteristic velocity is defined. And typically we can find a characteristic velocity V0. So if that's the case, let's look at our dimensionless groups. The first one in the equation of motion would be mu over rho V0 L0. This is exactly what? This is actually the 1 over the Reynolds number. Okay, and then if we look at the second term of the equation of motion, the buoyant term actually can be neglected. T1 minus T0 over L0 V0 square. Typically, for a forced convection problem, the buoyant force or the buoyant term really doesn't contribute much, and we will neglect that. For the equation of energy, the first term, which is thermal conductivity over L0 V0 rho Cp, this is actually what? This is actually 1 over the product of Reynolds number and the Prandtl number. And finally, the last term, which is mu V0 equals over L0 rho Cp T1 minus T0. This actually equals to the Brinkman number over the product of the Reynolds number and the Prandtl number. Okay, so before we continue, let's take a look at the physical interpretation of the dimensionless groups that we're seeing here. So we have the Reynolds number, the Prandtl number, and the Brinkman number. So really quick, let's take a look at the physical interpretation here. Of dimensionless groups. Okay, so first let's take a look at the Reynolds number. So the Reynolds number equals to rho v naught L naught over mu. And it actually is equal to rho v naught over L naught over mu v naught over L naught squared. So it's actually the ratio of inertial force over viscous force. Okay, so that means if the Reynolds number is large, then the inertial forces dominates. And if the inertial forces dominates, then the first term on the right-hand side, the second term on the right-hand side, that's dealing with the shear stress, actually it's going to be very small and maybe even negligible. Okay, so the Reynolds number is a good indicator of whether your system, whether viscous forces are important in your system or not in the equation of motion. Okay, and now also let's take a look at the Prandtl number. So PR. Maybe I should also put Reynolds number. Reynolds number. The Prandtl number, let's take a look at that. The Prandtl number is defined as what? It's defined as mu times Cp over thermal conductivity. It actually equals to the thermal diffusivity, the kinematic viscosity or the momentum diffusivity over the thermal diffusivity. So it's a measure of what? It's a measure of the momentum transport by viscous mechanism over the energy transport by conduction. Okay, so the Prandtl number is just solely dealing with the molecular mechanism. Okay, so what that means that if in the equation of energy, if the Reynolds number is very high, or if the Prandtl number is very high, then the first term of your energy equation of energy might also be negligible, depending on its relative contribution to the second term, right? And so we can also take a look at the Brinkman number. So this is Prandtl. And finally, the Brinkman number equals to mu v naught over L naught squared over k times T1 minus T naught over L naught squared. And it's also a measure of what? It's the ratio of heat production by viscous dissipation over heat transported by conduction. Okay, so this is Brinkman number. Okay, so the Brinkman number and the Reynolds number and Prandtl number determines whether the system has a lot of energy transport by viscous dissipation. Okay, so if the Brinkman number is large, that means the heat production by viscous dissipation is very, very large compared to the heat transported by conduction. So it cannot be dissipated by conduction. But if you still have a huge Reynolds number and Prandtl number comparatively, then these numbers can tell you whether the energy transport in the system is dominated by conduction, by convection, conduction, or the viscous dissipation here. Okay, So this is the most general case in forced convection. Again, in forced convection, the buoyant force typically are neglected. So the second bracket in the equation of motion usually you don't need to consider that. Okay. Now let's take a look at case 2. So case 2 is an intermediate between forced convection and free convection. Let's take a look at that. So case 2, which is intermediate. So we can still use a characteristic velocity, meaning that there are still some forced convection giving us a characteristic velocity. So the terms in the brackets basically are mostly the same. So let's take a look at that. So we still have the Reynolds number term. So we still have mu over rho V naught L naught. That equals to 1 over Reynolds number. But for the buoyant term, it's now non-negligible, so we need to consider that. So G L naught beta T1 minus T naught over V naught squared. This would be the Grashof number over the square of Reynolds number. And the rest would be the same. So for the energy equation, we still have, the thermal conductivity over L naught V naught rho Cp. This still equals to 1 over Reynolds number and Prandtl number. And the second one is still regarding viscous thermal dissipation, would still be equal to Brinkman number over the product of Reynolds number and Prandtl number. Okay, and now let's take a look at what is the Grashof number. So the Grashof number, hopefully I have this here somewhere. So the Grashof number is equal to G beta T1 minus T naught over L naught cube over the kinematic viscosity square. So it's basically a measure between buoyant force and viscous force. So basically, if the Grashof number is large, then the buoyant force can exceed the viscous drag. So meaning that it's easier for free convection to happen. But if the Grashof number is small, that means you have a strong viscous force that's going to stop free convection from occurring. Okay? Okay. Now let's look at case 3, where we have free convection instead of forced convection. So case 3, this would be the first case for free convection. And a major problem for free convection is how would you define a characteristic velocity? So characteristic velocity. Okay, and because typically for a free convection problem, there's no plug flow or whatever flow or pressure gradient that's driving a flow, right? So you do not have some V naught to begin with. Then how would one define a characteristic velocity? And this can be done by looking at the units. And if you look at the units of the kinematic viscosity, it has the same units as the diffusion coefficient. Okay, so we would try to use the kinematic viscosity over L naught as our V naught. And in this case, let's take a look at each terms again. So we have mu over rho L naught V naught now equals to mu times L naught over L naught and kinematic viscosity and rho, and that gives us 1. Now for the buoyant term in the equation of motion, now we have G beta L naught times T1 minus T naught over V naught square now equals to what? Equals to G beta L naught, not T1 minus T naught over kinematic viscosity square over L naught square. So it becomes G beta L naught cube T1 minus T naught over the square of kinematic viscosity and equals to the Grashof number. Now for the energy equation we have thermal conductivity over L naught V naught rho Cp, right? This now equals to what? Equals to K over L naught kinematic viscosity over L naught rho Cp. These cancels out, so you get the K over kinematic viscosity times rho times Cp. Okay, and if you look at the definition here, am I missing something? Yeah, so this now equals to K over mu Cp equals to 1 over Prandtl number. And finally, the viscous dissipation term for free convection can be neglected because typically free convection have a very small velocity gradient. So the viscous dissipation, because you don't have strong velocity gradient, that means you have very little heat dissipation through the friction of liquid layers, right? So let's say this can be neglected. Okay. And finally, for the case 4, which is the second case for free convection, so free convection B, which is looking at creeping flow. Creeping flow meaning that the left-hand side of the equation of motion can be neglected. Okay, so here you have a different choice of the characteristic velocity. Instead of using the kinematic viscosity over L naught, we were using the thermal diffusivity over L naught. And we have also the dimensionless pressure. Being the Prandtl number times the dimensionless pressure. Okay, so if you look at the 4 characteristic dimensionless groups, now we have mu over rho v naught L naught equals to mu L naught over L naught alpha rho equals to the kinematic viscosity over an alpha, and that equals to the Prandtl number. For the second term regarding buoyant force, we have G L naught square, no, not just L naught, beta, T1 minus T naught over V naught square now equals to the Grashof number times the square of the Prandtl number. And for the first term in the in the thermal conduction, actually it becomes unity. So L naught V naught rho Cp equals to 1. And again, the viscous dissipation term is still neglected because it's free convection. So great. So we have basically covered the 4 cases of the dimensionless form of equation of changes. So we're looking at case 1 would be forced convection. Case 2 is intermediate. Case 3 is the first case for free convection, and case 4 is the second special case for free convection. Okay, and you can see that depending on the different systems or different cases we're looking at, different dimensionless groups will appear. And the true advantage of using the dimensionless form of our equation of changes right here is that after defining which case is applicable, then we can determine the dimensionless groups in the brackets. Okay, we can determine the dimensionless groups in these brackets, and if we can determine the dimensionless groups in the brackets, then we can compare which terms are dominant and which terms are negligible, and that makes our analysis much easier, and it makes it easier without introducing much error. That's the most important part here. Okay, so for example, when we're looking at forced convection problems, it is pretty clear that the second term here would disappear. For forced convection, we will neglect the buoyant term. That's only related to free convection. So the first term here, the first bracket here is 1 over Reynolds number. So if today you have a very turbulent flow, this term may be neglected, and then you have a very simple case where you have a pressure-driven flow. Okay? And then for the energy equation, or equation of energy, you can look at the first term, which this is 1 over Reynolds number times Prandtl number. And this would be the Brinkman number over Reynolds number and Prandtl number. So again, so if you don't have a huge velocity gradient, you can just simply compare the Brinkman number, whether it's much greater or much smaller than 1. If it's much smaller than 1, you can neglect the viscous dissipation term, okay? And then you can consider all your energy transport going through convection and thermal conduction. If you have a system that has a really, really large Reynolds number or a really, really large Prandtl number, then even the conduction term may be neglectable, or it may be negligible. Okay, so this is a very useful, you can kind of say it's a very useful tool to quickly analyze your system, whether which terms are important to consider, which terms are not. Okay, so I think we will have a break here, and we will continue maybe with some examples to show you how powerful dimensional analysis can be.